Hello, everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding physics. So, today on General Physics 1, we want to talk about gravity, and the cheat sheet will be in the description below. So, first, we want to talk about the history behind the law of gravity. So, first of all, there was this guy named Copernicus. During his time, people thought that the Earth is the center of the universe, while the sun is while the sun is while the sun is rotating around Earth. But after certain thoughts, Copernicus realized that the sun is the center while the Earth is orbiting the sun. And this is the first development into understanding gravity. Because without this thought, people won't even think that gravity even exists. They will just think, well, 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 the planets move like this, and that's the only thought. They don't care about what creates this motion. And so after that, Kepler realized that realized that that the orbit of planets can be described using three laws. The first is the orbit is elliptical with the sun in the center, in the foci. This is th- this is one of the things that Galileo realized. And so and so technically this is not the sun. Instead it is the bigger object. So so basically if this is the sun, this will be the earth. The orbit will be something like this, while like these 2 points represents the foci, and this will be the sun. That's the first law. The second law was the area of a trajectory to the foci is the same. If the area of a trajectory to the foci is the same, therefore the time the time it takes is also the same. So 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 what this means is that if you have an ellipse, and then this is your sun, let's just state that the Earth is orbiting in 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 this direction. And so if you measure the area from here to here, is the same as the area from here to here. So basically, if these two guys' area is the same, that means the time is also same. Meaning that if the object is from here to here, it will take the same time for an object from here to go to here. Lastly, the square of the orbital period is proportional to the cube of the semi-major axis, which I will denote as A. So basically this means is that if you have this guy here, This long side here is called the semi-major axis. Yeah, technically it is twice of the semi-major axis, and so this length will be the time cubed. Yeah, basically it is proportional, stating that if you actually make the length much more longer, you would you would realize that its time would go into something like 3/2, like yeah, the period. And so these are the Kepler's law, and this can be derived through through vector calculus, in which I won't really describe much, and so you could actually prove this with calculus, but also Newton's law will also describe this, but only using one formula. And so we want to discuss about this Newton's law of gravity. Newton's law of gravity, which is what we will call as universal gravity. So the way that you will actually try to find the universal gravity, no, sorry, the universal gravitation is that the F equals to the G multiplied by the first mass multiplied by the second mass divide the entire thing by the radius squared. Technically, this is the distance. No, it is the displacement of the object. And so this is the force. Well, technically it is not really the force, it is the magnitude of the force. So technically it is the absolute value of the force. And so what is the direction of this force? Well, the force is going inwards. So basically if I have the sun here and then let's say that I have an object there, this object will gonna go towards the sun, while the sun is going to the earth by the by Newton's third law. And so you could write this to be, let's just state this direction to be r hat, in which it is the position unit vector. And so the way that you could write the force is the negative g m1 m2 over r squared r hat. But we will only focus on the use of this formula instead of the vector one. So you would already know what is the mass of the first object, and you might also know what's the position of of the object relative to the other. But the thing that you won't really know is g. The g here is called as the constant of universal gravitation. This number is about 6.67 times 10 to the power of negative 11 newtons meter squared over kilogram squared. So if you try to plug it in into this formula, you would see that the units will make sense. It's like kilogram times kilogram. So yeah, it will later cancel out with the bottom one. And then the bottom side will be meter times meter, which will later cancel out with the top side. And so the units will be in newtons. And so this is the value of the constant of universal gravitation within a three significant digit. So after we have already talked about this, we want to talk about a a special case. in a orbital motion. So the way that we'll actually try to derive this is that we'll just assume that we have the sun and then we have an object here and it is moving with a constant speed. So so what it basically means that that yeah, it has a constant speed, meaning that it is in a circular motion. Circular motion. So the way that I'll actually try to derive this is by using Newton's law. So first, we will just actually look at the object here. It is being attracted with a force, and then it will have a certain velocity. So we can write the F equals to ma, and then not only that, we have already figured out that from mathematics, for a circular motion, the movement has to be v over r squared. No, sorry, is that correct? Meter. No, sorry, my bad. It is v squared over r. So what is the F? The F is so the F is already known to be g times m. Multiply that by m over r squared, and this will later equal to mv squared over r. So basically, this object has a mass of small m, while the big object has the mass of big M. And so if you try to do the mathematics, you would later figure out that the v is the square root of gm over r. And so doing unit analysis, we would have Newton meter squared over kilogram squared. Multiply that by kilogram divided by the r. What's r? R is meter. So we would have Newton meter per kilogram, the square root of that. And so the Newton is kilogram meter per second squared. Multiply by meter over kilogram squared. No, sorry, kilogram. And so the kilogram will cancel out, and you will later have meter per second. So the unit makes sense. So at least that we will know that this is our answer by units. And and this is the speed of a object in a circular orbit. This only works in a circular orbit. So okay, we have already figured out this. So we could also ask the question, what about its period? So the way that we'll actually compute the period is also by using the results that we already have. So if we have the v here to be square root of gm over r, and then we know what is the circumference of this orbit, we will just state that to be the length. The length would be pi. The distance here is r. It is 2 pi r, 2 pi big R. No, sorry, let's just actually write it with small r. Let's just be consistent. 2 pi r. So the way that you will actually know how long will it take for an object to do one full cycle is what we call as the period. So the period, big T, will be the length over the velocity. So basically this comes from basically the distance equals to the speed, multiply that by the time. And so this is basically the same, but then you do some arithmetic arrangement. And so trying to write this down, we would figure this out to be 2 pi r over the square root of gm over r. And so this might seem to be a little bit chaotic, And so the way that I will actually write this is to be t squared. And this will later be 4 pi squared r squared divided by gm over r. And so this is much more tidier. And so you can write this to be 4 pi squared r cubed divided by gm. And this basically agrees with Kepler's law. This is Kepler's law, Kepler's third law. So 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 Newton's law agrees with Kepler's law, which is a good thing. That means that Newton didn't do anything wrong based on his current observations. So 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 we have already talked about a circular orbit. But then what about if the orbit is elliptical? This is this is a little bit harder. And so I won't really describe it here because this will require further mathematics. But you can actually do this using a simulation, which I will later show how I was able to create a object spinning like 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 a orbit of the solar system. So for a elliptical orbit, I want to describe a little bit of its technical terms. So first, there is something which we call as the perihelion. This is where it is at its closest distance, closest approach, while another one, which we call as the aphelion, is the furthest. So the way that we'll actually uh, define this is by using a elliptical orbit. In here, it's the sun. From here to here, this is what we call as the perihelion, while from here to here is what we call as the aphelion. It is basically like the minimum and the maximum distance. And so those are for closed orbits in which the object will go back to its initial position after a certain amount of time. But then there are certain conditions in which that you could create a system in which it will return back to its original position, and that is what we call as a open orbit. For example, if you have an object, it will later gonna get spit out and never ever gonna return back to its initial position. And so the way that you could actually try to find this boundary condition is by talking about its energy, which I will now discuss. So we want to talk about the gravitational energy. So the way that we'll actually try to derive this is by using the definition, which is the negative FDS. So let's just state that we have the Earth, and then we have, let's say, a bowling ball from this point to this point, from A to B. And we want to find what is the force, no, sorry, what is the energy needed to move this object from A to B. So the way that we'll actually do this is that if we move the object from A to B, this will be the negative of the integral from A to B of the f ds. We know the f to be in this direction, while the ds is going in the opposite direction. So we would know that this will later cancel again to give us a positive sign. So let's denote this to be dy. And then we'll also have the gm1 m2 over r squared. So this will later, if you if you try to do the integral, this will later be gm1 m2 over r, the negative, from B to A. And so this is basically the negative G M1 M2 over B minus the negative G M1 M2 over A. And so this is what, and so the way that we'll actually try to define this is to actually state that the potential energy at infinity will be zero. Because if you actually plug it in here, putting the R to be infinity, this will later result into a zero. So basically, you could define what this guy is. It's UB minus UA, which will later make sense. And then we'll state U at infinity to be zero. And so you could write that that the U of an object in R is negative G M1 M2 over the R. And so this is one of the important equations for you to remember when dealing with potential gravitational potential energy. So, using this idea, we could now define what we call as the escape velocity, in which it is the amount of velocity needed for you to escape from the gravity. So, so the way that we'll actually try to solve this is that if you have the v escape, no, sorry, we will uh, we will use uh, we will use the definition of energy first. So let's just state if you have an object here, and let's just state that it is starting from a place. Let's just state there. This has a distance of r, and this will have potential as well as kinetic energy. But then, if you try to escape this gravitational force, this will later mean that the u will equal to zero, while it still have the kinetic energy. And let's just state that the kinetic energy will be minimum, or we could state that to be zero, if that's the best case. No, sorry, if it is the minimal that we can do. So we will first try to use the u plus k in here, which is negative g m1 times m2 over r. And so the easy way for me to write this is to actually use big M and small m, big M and small m. So this will be big M, this will be small m, plus half mv escape squared. And so v escape is the initial velocity that you need to get out of this place. No, sorry, to escape of the gravitational well, which we will try to figure out. And this will later is hoped to be equal to zero, in which it is basically the minimum. Or you could technically state that this is greater or equal to. We'll just write it as this. So if we try to use this, we would later obtain that you could actually divide both sides by m, and then we could multiply both sides by 2. We would get the v escape squared to be greater than equal to 2gm over r. And so if you basically take the square root of this will be the square root of 2gm over r, where the v should be positive. And so this is what we call as the escape velocity. And so yeah, technically this is should be an equal, but then any velocity higher than the uh higher higher than the escape velocity will also well escape the gravitational well with a extra amount of velocity to go elsewhere. And so this is one thing that you need to remember is that because because this is used in this is used in lots of different applications. So we have talked about the escape velocity as well as talking about the gravitational potential energy. So now we should also try to discuss a little bit about the energy in a circular orbit. So last time we have figured out what the velocity is for a orbit for a circular orbit. So we could first write the first term, which is negative g big M small m over r plus half m the v squared, and so writing this down again, we could write gm big M over big M small m over r plus half m with the velocity to be square root of gm over r, square root of gm over r. And so we would later figure out this to be negative half gm over r. And that is the energy for a for for a circular orbit. So it's negative g big M small m over 2r. So we have talked about the force, and so people might think like, how is there a force even though that there is no object connecting this object with another? And so this is where the development of the idea of fields comes in. So in here we want to talk about the gravitational field, but first I want to define what is a field. So a field is a property of space, and it is a vector quantity, and it is a function of time and space. So what does this mean? So basically a space will have a certain position, and then during a certain time it will have a certain field which corresponds to a direction. And so there are lots of different types of fields. One of them is the magnetic field, the other one is the electric field. But in here, we want to talk about the gravitational field. So this concept interacts with, if you have an object and it is interacting with the gravitational field, how will it move? So the way that we'll actually define what a gravitational field is that we'll just actually write this to be F vector divided by M. This is what we call as the negative. No, sorry. This is what we call as the gravitational field, and then plugging in Newton's law of gravity, we would later obtain negative gm over r squared in the r hat direction. And so this is what we call as the gravitational field, and it is a vector. And notice this. You could also write f vector to be mg hats. So does that mean that this g vector is the acceleration? The answer is yes. The fact is, the force is described by the field, and this gravitational field resembles that the force is always parallel to the field. Therefore, you could actually understand where the force is going. But this is not always true for every single fields. For example, in the electric field, the thing that is actually describing, no, sorry, the electric field describes the force that it is, no, sorry, it describes the direction as well as its magnitude as long as you know its charge. Same thing with the magnetic field. You could know its force if you know the charge as well as the velocity of the particle. And so you need to separate your mind between fields as well as its force. So, so a field is a object that describes how an object will move across space. So we have already talked about all of this. We want to talk about one of one of the examples that is normally used when talking about gravity, which is the orbit of the moon. So for for our example, we will use astronomical data to solve for the orbit, to solve for the period of the moon, and which I hope this to be about 1 month. So let's get our data in first. So here are the data that I have of the mass of the Earth, mass of the Earth, of the Earth, as well as the distance from the Earth to the moon. And by the way, this distance is the average. We won't we won't really care if there's a perihelion or the aphelion. So we'll only use these data to try to find what's the orbit of the moon. So we have already figured out the orbit of the moon. The t squared would be 4 pi squared r cubed over gm. So let's just try to plug all the values in first. But before that, we also need to make sure that our units make sense. So first in here, we realize that this r is not really in SI units, while we want it to be in SI units. So let's just write this down to be 3.84 times 10 to the power of 8 meters, as this is the number that we will actually use. So we have already gotten this value. We'll go ahead and try to compute the value of the period straight away. So you could just straight away plug it in into the calculator. It will be 4 pi squared. Multiply that by the r cubed. The r here is 3.84 times 10 to the power of 8 to the power 3, and everything is divided by the constant of gravitational acceleration, which is 6.67 times 10 to the power of 11. Was it? It's 10 to the power of negative 11. Multiply that by the mass of the Earth, which is 5.97 times 10 to the power of 24. So we obtain the value to be 2.37 times 10 to the power of 6. Okay, so the value itself doesn't really seem to be 1 month, but this unit is still in seconds, so we should try to convert this into days or possibly into months. So first thing is that we could actually convert this into minutes. So we know in 1 minute there will be 60 seconds. So doing the computation, let's see if I can do this correctly. It will be 6, that will be 357, 935. So it's 0.395 times 10 to the power of 5 minutes. Writing this again, it's 3.95 times 10 to the power 4 minutes. And then we can convert this into hours. So we should divide it again by 60 to get this in hour per minute. So this will later be, let's see if I can compute this correct again. 6, so it's 0.6, 35, 550, 450, we'll put an 8, 8, that will be a 48, and then 20 will be about 2, so we could just round it down to be this value, times 10 to the power of 3. And this is basically 6.58 times 10 to the power of 2 hours. So it's about 658 hours. And so converting this into days, in one day there will be 24 hours. And this is where I need to use a little bit of mathematics divided by 24. So this will be 2, is it 2? No, yeah, it's 2. That'll be 48, it's 0.2, sorry. 48, subtract that, it's 178. Multiply that, 6, no, 7, 8, no, 7. It's 7, so it's 8, 2, 14, 16. 10, let's just make a precision. Let's make it into 3 significant digits. 5, 4, this is 4, yeah, it's 4. That's 96 over 40. And yeah, this will be 1. So this will be 0.274 times 10 squared, which is 27.4 days. And this seems to agree with our observation. We know that the moon revolves about 1 month. And so if we actually try to also search for the orbit of the moon, it is it is written in the American Scientists website. It is 27.3 days, which is very close to our data that we actually uh, compute. And so we could actually use a use a simulation to actually figure out what's the period. And so the way that I write this program was to actually do something called a numerical integration, in which I take small steps and then applying the change. And then because this is not a math course, I will leave it for you to actually to research on your own and 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 also try to program this yourself. So now I want to show you the results. So here I have already simulated the orbit of the moon relative to the Earth. You could see that it is spinning and it has a period of about 27 to 28 days, which is the amount that we actually predicted using only computations. And so this is one of the practical applications in which you could use Newton's law of gravity to actually figure out the motion of a system of body. Let's say the solar system. You could model each by using only Newton's law. And so if you're able to code it out, you can just go ahead and do it, and you will later find a beautiful simulation that is basically representing the real world. So thank you very much for all of you guys who stayed until the end, and I wish this video helps you to understand physics much more better. So if you want more of this, please subscribe to this channel, and I will see you on the next video. See you later.